Here's an interesting item that I picked up a while ago at an auction. It's an antique precision resistance box made by Gallenkamp in London. Antique because I believe it to be over 100 years old. As far as I can tell, it was made around 1910. And precision because it appears to have a tolerance of 0.1%, which is pretty good even by today's standards, and probably very good by 1910 standards. Still wasn't the top of the line. There's other models of this that are 0.05%, and no doubt standards, laboratories and whatever had much better than that again, but still 0.1% is nothing to be sneezed at. So what it is basically a set of resistors in series, 12 of them, starting here, all in series back to here. These are shorting pins, so each one of these shorts out the resistor underneath it. So if all the pins are in place, you should have 0 ohms, and then you can pull out as required to get the resistance that you want. And they're 500 ohms, I think, 200, 200, 100, 50, 50, 20, 10, 10, 5, 5, or 5, 2, 1. This is 1 ohm, this one, that's 500. Not sure of the others, we'll find out. And as you can see, there's markings, but only 4 of them are still there. I've got 5 more that have fallen out, but 3 are missing. And I got this thing for, I had to beat off one other bidder. I got it for 20 bucks. I also scored this Sinclair DM2, which is a bit of a classic, for only $5. Wasn't a bad day. To date this thing, the only reference I could find was a catalogue from Gallenkamp Company from 1910 on archive.org, and it's a very interesting PDF file, and I found things that look exactly like this in it. So that's why I think this is from 1910. Hopefully when we open it up we'll find some dates in there. That would be really good. But I'm not holding my breath on that. Let's have a look at the catalogue entry for this thing. So here's the Gallenkamp catalogue from 1910. I can't find any date inside this PDF of 2,000 pages, but the archive.org entry says it's from 1910. An amazing document actually. It's big, 174 meg, but it's probably worth downloading it. I'll put a link to it in the description below because it's an interesting read. So there's Technico House, which is the headquarters in London of Gallenkamp and Company Limited. Showrooms, various departments. Now, what this mob didn't have, well, you wouldn't need. There's just so much stuff in here. So there's about 100 pages of other stuff, but there's a good 1900 of actual catalogue with multiple entries of products per page. So you can just see how much stuff these guys had. The range is breathtaking. Yeah. And they didn't just have all the equipment for your laboratory, they could also fit it out for you. They had all your cupboards and benches and tables and things you might need for your laboratory. Even the kitchen sink, the laboratory version. Now, yeah, enough of that. Let's look at the only entries I found for the device that I've got. Right, here's 2 pages with 2 devices that appear quite similar to the one I've got. Number 14244 and number 14340 or 44, which is different to the model number on the thing I've got, number 1386, but you can see it's the same sort of device, the same terminals, the same plug connections, the same box. So that's why I think this is from about the same era. Now they come in different models. You see here we've got 16 coils, 12 coils or 8 coils. So this is the 12 coil one, each coil being
a wire wound resistor. And so for 12 coils, £4, 12 and 6 Australian dollars in 1966. Pounds turned, £1 became $2, so yeah, $8, and paid probably double, but that's not bad for inflation. And looking at this page, there's a bit more detail. You see here it says second adjustment. I think that refers to here, where you can see we've got first quality, second quality and students quality. So that's why I think, and this is from 1 ohm and up, so that's why I think that this is the 0.1%, and the first quality would be 0.05%. And they've got numbers on there, might be just drawn in, might not be what it actually looked like. They don't have those little ivorine inserts, and maybe that was a later addition, later embellishment, these ivorine inserts. They were, possibly this thing's a little bit newer than those, but why has it got a lower catalogue number? Not sure. Anyway, looking at some more detail down the bottom, we can see that the student's quality and the second quality use constantan resistance wire, whereas the first quality uses manganin. And we got the 1 to 500, 12 coils. So if all the plugs are pulled out, the series resistance adds up to 1.11k. So £4, 12 and 6, same price as on the other page. But if you went for first quality, it nearly doubled, just because of the manganin wire, or maybe there's a lot more effort put into construction and calibration. So yeah, that's interesting. I think now it might be time to have a look inside.
Right, let's take these 4 screws off. They're wood screws, so there's no inserts. I have cleaned this up a little bit. I've tried deoxidizing, run deoxide on these brass terminals, and they've come up a bit. Obviously there's still a lot more cleaning to do. I wanted to get them clean so we could get hopefully accurate measurement of resistance when we get to that. But first we should look inside. It'd be really good if there's a date in here. Okay, opening it up. Oh. Very nice, all wax covered. Looks rather nicely made. Can't see any dates though. Nothing in there. No. Nice mahogany box. Yeah. So that's pretty straightforward, isn't it? Just 12 coils, and each plug shorts out each coil. All in one long chain. That one looks like it might have had a bit of over temperature at some stage in its life. That's this one here. Not sure what value it is, might be a 10 ohm. Oops, plug fell out. One of the things I wanted to find out opening this up was if these went through to there, but they don't. So that means to clean these up, I can probably give everything a good squirt of deoxit to try and get the resistance when they're all plugged in down to 0 ohms. So okay, that's what's in there. Nice. Except perhaps a bit of cooking's gone on this one. If that one had been cooked excessively, you might expect some drips of wax to be in there, but there aren't, so that's probably a good sign. Okay, I'll put it back and connect it to a meter and see what we can read. It's a little bit cramped here where I've got these meters, but I'm in the bloody light, aren't I? So I've got some leads, not gold plated, not low thermal EMF, but oh well. These terminals have 2 parts. There's that bit that just fell down, knob, and then there's a disc. Type 1. So I'll put the sense wire on the bottom and clamp it down with the disc and then put the fourth wire on top of that and clamp it down with the knob. And these are nice big solid lumps of brass, or I think it's brass, I don't know, I'm colourblind, could be copper, I don't know how to tell the difference, but nice and big, so lots of thermal mass to mitigate any thermal EMF problems. So we'll put that there and that there. Now we have an alternate light source, that's a bit better. Okay, so they're the sense wires. So we'll stick them in here. And now the force wires. So if there are any temperature differences in there, hopefully they'll disappear fairly soon with all that metal. Right, 0 volts, good. Right, let's go to 4 wire ohms, 103. What? Push all these plugs down, that's a bit better. Yeah, so there's obviously contact resistance problems there. Yeah, I don't want to scratch the box up, so I'll operate it like that. So I think it might be a good idea to get some dioxin into this pretty soon, but okay, we've got 11 milliohms and may as well go for the full 6.5 digits. Alright, so pull out this one, which should be 500 ohms. Yeah, I'll get rid of that, I'll make it 10 power line cycles. It's too slow otherwise. 500 ohms for that one. 200 for that one. Another 200. 100. 50. 20. Going to the other side now. Another 20. You get a 5, 2 2s, a 1, a 5, 2 2s. So this should be a 10. Yep. And this should be a 5. Yep. And then 2 2s. Yep. There's one. And there's the other. And 1 ohm. Yep. So 500, 200, 200, 100, 50, 20, 20, 10, 5, 2, 2, 1. So the 5x and 1x you get 1 of, but 2x you get 2 of. Right, so obviously there's contact issues here. I'm going to stick some dioxin on all these things and leave it for a while and see how much better this gets. So the absolute rock bottom I can get with. There we go. Anyway, I'll put some dioxin on those and see how less dependent it becomes on twisting these things tight. Right, give it a good go with the deoxit and took them out and cleaned them up. I've taken out all the deoxit, so maybe it could be left in there, I don't know, but it doesn't seem to be too affected by twiddling these so much now. And not as if that's exactly clean, but see there's 200, one of these wasn't connecting. And there's also some goo I just noticed on there, some sort of a, it was wax, it seems harder than wax. Something dribbled, looks like it dribbled out of there and down here. So you've got to be very careful with making sure that things that look like they're connected are connected. 200, that looks like it's in there, but it's not. Just a few milliohms. Take out the 500. So it's 500.6 something ohms. 1% of 500 is 5. 0.1 is 0.5, so it looks like about 0.1%. Now, these were 1910 ohms. What the ohm was redefined in 1990, but only slightly. I think so little that it won't affect what we're looking at here. And then this thing was made before 1990, so is that calibrated to, who knows when this was last calibrated? Maybe it says there. No, it doesn't. So was this calibrated in 1990 ohms or pre-1990 ohms? There's also a fairly large change in the ohm in the United States in 1948, but that's only because they had their ohm wrong. Shouldn't be affecting this made in England. So 200.22. Take this one out. 200.43. So those 200s aren't the same. Okay. This 20 is 20.03. 20.01. So they're not the same. 2 ohms. 2.01. Try the same one again. 2.01. Other 2 ohm. 2.01. A bit more the same. 2.01. And the 1 ohm. 1.01. This is the one that was cooked. The 10 ohm still seems to be 10 ohms. Take them all out, we should have 1110. 1100, shouldn't be 1111? Yeah, 1111. So we want to get a K, that's 500 plus 200 plus 200 plus 500. That should be 1,000, but it's 1.37 too much. 1% of 1,000 is 10 ohms. 0.1% is 1 ohm. So we're close to the 0.1%. Might be a little bit out. Not sure what to make of that. And look, see, this 200 is sticky. He needs more deoxit, doesn't he? And that's the one that's got the goo poured out of it. So that's interesting. What can we do to test this thing for stability? Let's try, let's just look at the 100 ohms. Try and get this as low as possible. So at least it's not very sensitive to how hard you twist these things anymore, so the deoxit has done something. Except this one, which we can't get rid of that last 0.1 yet. It's not there, so that 100 ohms is just not 100 ohms, it's 100.1. Maybe that is due to some, standards changing somewhere along the line. I'll leave that 100 out, so I'm on 6 digits with 100 power line cycles. We've got 100.1039, and I'll just leave it going for maybe a day or two and just see how that varies from time to time. 100.1 ohms. It's definitely not 100 ohms. Not by, as measured by this thing anyway. I'll let it run for a couple of days and I'll just note what values I see there. 100.1035. I've been a bit lazy and I've left it for about a week, and we're at 100.1035, I think, and within the first day it drifted down quite a bit to 100.0 0.09-ish, and the lowest I've seen it get to is 0.0863 and up to 0.0914. So that's a range of whatever. We'll work out the percentage in a sec. And I've had this other meter powered on the whole time, so it's nice and warmed up. And let's just plug these leads into the top meter and see what that one says. Leave that running for a while. And it's on the same settings, I think. All the lights match. Yep, 100.0948. So, you know, they're different, the 2 meters. Be nice to know which one was right, wouldn't it? Anyway, I'll leave that go for a while. I'll start noting the ranges that it goes through on this meter. Well, that's been sitting there for about another week using this top meter. It's ranged from 100.0893 to 100.1054, and the temperature in here has been fairly stable. It wouldn't have moved more than absolute maximum 5 degrees centigrade Celsius from it's probably only moved 23 to 26 in the time that's been running, so I haven't got an actual temperature measurement going, but yeah, that's what it would be, I imagine. So it's not very rigorous, of course, but I might be able to do something about that. I've got a bunch of these connectors which plug into the GPIB port on the back of all these instruments, and there are projects on the EEV blog to interface these with an Arduino so that the PC can control all these things and log stuff coming out of them. So I'll play with that. I'm also getting one of those thermoelectric coolers, but it's also a heater, so it can go up to maybe 65 degrees C and down to 15 degrees below ambient. So should be able to take that to 5 degrees or 10 degrees Celsius, and with better insulation than the box comes with standard, maybe even better. And I could put this in there and keep the temperature of that absolutely rock solid, and see how much of an effect the external temperature has on this meters while the resistance and other resistors as well, with that at constant temperature. See how much these vary, because I don't know which is varying more. Where is this variation? Is it in this meter or is it in that? So it'd be interesting to play with that. And that thermoelectric heater box potentially could also make some sort of interface to it to control it externally, so we could log it through cycles of temperature cycles from 5 degrees to 35 degrees and see how things react, see how reproducible it is, whether they follow the same curve up and down. Yeah, just things to play with in the future. So there's the Gallenkamp resistance box. Hope you found that mildly interesting. Catch you later.